There we go. So when we take a curve and we zoom in enough, the curve eventually will become straight, right? Now, if we were to zoom in one more time. Going down. Okay, so say we've got this line, right? Not only does the curve become linear, but say I wanted to find the equation of that line. What do you think that the equation of that line would be? The same as?
Same as derivative.
Y equals x squared.
The linear approximation of that point.
So I squared that.
Alright, I'm going to try
Replace
something.
the decimal number with
Okay.
x approaches this.
I'm going to go to my draw menu,
Limit is x.
and I'm going to draw a line tangent to this function at point 7. So,
Well, it's on top.
whoa. By the way, do you know your calculator will give you an equation of a tangent line? Right? Okay, so the equation of the tangent line at point 7 is 1.4x minus 0.49. Anyway, the linearization of the function is actually, if you were to write the equation of that line at a point, it would be same as the line tangent to the function at that point. Does that make sense? Because if you draw a curve, if I draw a curve and I draw a line tangent to the curve at a point, well, if I were to zoom in on that curve, the more I zoom in, right, the tangent line and the curve are like right on top of each other. Does that make sense? Now, why do we need to know that? Well, because in tangent line approximation or linear approximation, there's got a bunch of different names for it. When you're using the tangent line to approximate values on the function. So if you just kind of pretend, say I've got some function, and say I don't know, let's just pretend I can't use this function for some reason, but I have a line tangent to this function at some point. Say I want to know what the value is on the function here, but I don't have a function to plug into. I can plug into my tangent line and get a fairly decent approximation for a value on the function. Now it's got to be close to the point of tangency. I'm not going to use this tangent line to approximate function values over here, right? Or over here. It just would be silly. But if I pick up a point that's close to that point of tangency, then the value on the tangent line is very close. It's a very decent approximation for the value on the function. Now all that being said, in a nutshell, all we're doing today, if you're writing down these notes, you're wrong because that's after, we have another example first. So anyway, all that being said, here's all we have to do today is we're just going to find an equation of a tangent line and plug numbers into it. That's the essence of the lesson. Yeah, it's really not a difficult topic. So all you're doing is you find an equation of a tangent line and then you plug numbers into the tangent line instead of the function. All right. So here's our first example. So if you want to label this, you can call it linear approximation, or you can call it tangent line approximation.
I call it linear.
All right. Some people call it local linear approximation because you're using the linear approximation in a localized area on the function, right? So lots of names, lots of names. So here's our first example. Write the equation of the line tangent to f of x equals the cube root of x at x equals -8, and use it to approximate f of negative 8.1. So in your groups, I want you guys to take a minute and write the equation of the line tangent to f of x at x equals negative 8. What two things do you need?
Point.
Point and a slope. Where do you get the point from?
Plug it in.
Plug in where? Original function. Where do you get the slope from? Derivative. So go ahead and do that. Take a minute. Keep it in point slope form.
That's 2, right?
So now we need to get the points. So, degree of negative 8, is that negative 8? Positive 2?
Oh no, you can't take a negative.
So is it 2 odd?
No, because it's a cube. No, because it's a cube. So yeah, it's just negative 2.
Negative 2, because negative 2 times negative 2 times negative 2 is negative 8.
Yeah, so it's negative 2.
So it's negative 8 comma negative 2.
Yeah.
And so what do you do with negative 8?
Then
Plug it in. Oh no, you gotta write the... Take the derivative, bro. Take the derivative.
Yeah, I did.
Function.
That's 1/3 x to the 2/3, negative 2/3.
X to the 1/3. Isn't it just x to the 1/3?
Yeah, but that's not derivative.
Oh, so it's x to the 1/3, then 1/3 x, so 1/3 minus 1 is negative 2/3.
Wait, so is it 1 over 3 1/3 the cube root of x squared?
Yes. Or f(x) equals x to the 1/3.
Is this what you got?
Like that.
Yeah, that's it.
1/3
That's
x.
it. Yeah.
1/3.
So now you plug in negative 8.1 in there? Or no?
No, that's just a slope. Isn't it?
So now you need y minus, y plus 2.
Yeah.
Equals,
I haven't finished writing.
That.
yeah. Isn't that just the slope?
That's the slope.
Plug in.
I don't know, I'm just trying to find the slope of the
Yeah, no, that's not the slope.
How do you want more fun?
So you have
Do
to
I have a
plug,
calculator?
Oh, yeah.
to plug in 8.
Wait, 8
squared, that 64.
No, that's 64.
64 cube root 64.
No, wait. You're using this derivative, you plug in 8.
We don't plug in 8.1.
You're doing that.
You would square it
So
first, and then
64,
you
what's 64? For the cubic root of 64.
All right.
So it's 4 times 3, that's 12.
Okay.
1 over 12.
So first thing we need is the point.
12. Oh yeah.
So we need f of negative 8, which is the cube root of negative 8, which is what?
Negative 2.
Negative 2. So our point is negative 8, negative 2, right?
Yeah.
Okay. The slope, we need f prime of x. X, how would I rewrite this function in order to find the derivative?
X to the 1/3.
X to the 1/3, right? This is x to the 1/3. So the derivative is 1/3 x to the negative 2/3. Now, in order to write this, to find the actual value of the derivative, you want to rewrite back in radical form so that 3 goes down. So what root is it going to be? Cube root of x squared. Why did I put it on the bottom?
Because it's negative.
Because the exponent is negative, right? All right. So I've got that. I want f prime of negative 8. So it's 1 over 3 times the cube root of negative 8 squared. Do the root first. You don't have to square it first. You can do the root first. The cube root of negative 8 is negative 2. Squared is 4 times 3 is 12. Our slope is 1/12.
Yeah, but it's 1/12.
So our equation is y plus 2 equals 1/12 times x plus 8.
So what do you do with the negative?
All right, how many of you guys got that? Something like that? About half, a little over half.
I'll get my I got that.
Where did you guys go wrong? Did you get the point right?
Yeah, I got a point right.
Did you get the
I messed
derivative?
up on the derivative.
The derivative?
Connor,
Did you have the function
Yeah,
written
the
correctly?
equation we found.
I just didn't change it.
Connors.
I forgot to do like x to the 1/3.
Oh,
This price.
how do you do it then?
I don't even know. I was so. I just forgot how to do derivatives.
Okay, don't forget, when you have a derivative, you need something to a power, right, in order to differentiate. Yes.
Connor's birthday.
We'll take care of that once we,
Alright.
finish
Just-
this.
Oh, Connor,
we
Miss
can't-
Cantrell
All right.
needs a list of your accomplishments.
So, this first part is just,
My,
okay. We've written the equation of the tangent line. Now we have to approximate f of negative 8.1. So in order to find f of negative 8.1, we plug a negative 8.1 in for the x in our tangent line. So we have y plus 2 equals 1/12 times negative 8.1 plus 8. So y equals 1/12 times, this is negative 0.1, and then just subtracting the 2. So f of negative 8.1 is around 1/12 times negative 0.1 minus 2.
and we can just leave it like that.
And you can just leave it like that.
Okay.
You can convert this to negative 1/10, and you get negative 1 over 120 minus 240 over 120, so you get negative 241 over 120. But you could just leave it like this. Yes. All right, and that's it. Okay. So what we did, here's what we did. We had the cube root of x, right? Cube root of x, so we've got a cube root function, normally looks like that, right? We're over here at negative 8. Pretend that's the axes. So we're over here at negative 8. We found the equation of the tangent line. And then, instead of, we wanted the value on the function at negative 8.1, but instead of plugging into the function, we plugged into the tangent line.
So what is accomplished then?
Well, what's going to happen, the way that we're going to, there's actually some fairly decent applications for this that we'll get into when we get into AP problems. But for now, just know that we're going to present a scenario to you where you will not be able to find the function value, but you will be able to find the tangent line, and you'll just plug into the tangent line to approximate the function value. Okay? All right, good. One little warning I need to give you is that a lot of books don't write x as x for these problems. They use the letter A. So if you see something where they say A is negative 8 instead of x, just know that the A is the x value of the point of tangency. So tonight your homework is a worksheet because your own textbook does not have very much on linear approximation. So I just drew problems from several different sources. But just know that if you see A is just the same as your x value of the point of tangency. Yes?
If they say A, would they put f of A, or would they keep it f of x?
I think they'll use f of x.
That's dumb.
Wow.
Because A isn't a variable, it's a constant. So they're using A to represent the constant. And I don't know. Anyway, that's tradition. Okay. So just know, if you see A, it means the x value of the tangent point. All right, let's do one more example, and then we have one other thing to talk about, and then we're done. So it's a very short lesson. Moving the camera. No, it's really not. Okay. Now, once in a while, they'll give you a problem. I'm going to erase this, just rewrite it. They don't even give you f of x, or a, or x, or anything, right? All they say is, hey, fellas, use linear approximation to estimate 1 over 10.1. So from this, you don't know what f of x is, you don't know the x value, you don't know where the tangent point is, you don't know what to plug in, but we can figure it out, and it's real easy to figure out. So when you're handed a problem and you aren't told explicitly, here's the function, here's the point, this is how you find it. The first thing you do, there's always a decimal number. a number with a decimal, 10.1, 8.2, right? Negative 3.05, whatever. Yes, there's always a decimal number. You're going to replace that decimal number with the letter x, and that's your function. So for this one, we have that 10.1. So our f of x, if we replace the 10.1 with an x, our function is 1 over x. Because the 10.1 is what you're plugging into your function, right? So the x is where you plugged it in.
Okay.
Okay, so you replace that decimal number with an x, and that gives you your function. Next thing you do is you find the integer that's closest to the decimal. So for us, 10.1, what number is closest to 10.1? What integer? 10. That's like your a, right? We've been talking about a. So our a is 10.
Whoa.
So then, the third step is to do the problem. You write the equation of the tangent line, which we'll do in a moment, and then what number do you plug in? Just the decimal number. So you only plug in the 10.1. That's like the x value you plug in, not the 1 over, just the decimal number, the 10.1. Okay? So let's find the equation of the line tangent to this function at that x value. What two things do we need?
Point and slope.
Point and a slope. How do we find the point?
Original equation.
Original function. How do we find slope?
The derivative.
The derivative, right? All right. So in order to find the derivative of 1 over x, I should rewrite that function as what?
X and negative.
X to the negative what?
X and negative 1.
X to the negative first. I want everyone right now to find the equation of the line tangent to this function at this x value. You need another minute? You can talk to each other. It's okay. Compare your answers with your group mates. Make sure you match.
It's not water pressure. Size is always 1. This is always negative. Oh, the solid you haven't taken that test yet. Wow, slacker. Wait, that's the first unit. No, it's the second.
What is your
Negative 1 I know that. Well, negative 1 over x squared.
Hypotonic is like when you sell.
Okay.
Hypo and iso. Hypo, hippo.
Looks like there's some disagreement on the derivative.
That's easy.
I think we all have the function value. What's the function value?
1 over x.
So 1/10, right?
Yeah.
So our point is 10 1/10.
Yeah.
So now we need f prime,
Which is the derivative.
which is the derivative of x to the negative first. Tell me the derivative.
Negative 1 over x squared.
Okay, without simplifying, just
negative x squared?
negative x to the negative second, right? Negative 1 minus 1 is negative 2, not 0.
Right.
Okay? So we end up with negative 1 over x squared.
Right.
We want f prime of 10, which is negative 1 over 100. So our tangent line is
X minus 10, or y minus 1 over 10.
y minus 1/10.
Equals negative 1 over 100.
Uh-huh.
Times x minus 10.
Times x minus 10. Very good. Now we need to use the tangent line to approximate the function value at 10.1.
So plug 10.1 into the tangent of that equation that you just wrote.
That's perfect, yeah. So I plug a 10.1 into that equation. Y minus 1/10 equals negative 1/100th times 10.1 minus 10. So we get y equals negative 1/100th times 0.1 plus 1/10.
Wow.
And that is your approximation for f of 10.1.
Do you want us to simplify?
Swaggy.
No, I don't. I don't. Yeah. I am not having good things happen with people who are simplifying. So, yeah, let's just keep things unsimplified, and that's fine. Remember,
Appreciate
numerically
it.
equivalent to correct is correct, right? There's one more thing I need to teach you. Oh,
Oh, man.
man. Okay. One other question related to this topic that you might get asked from time to time is the approximation, where did I put my here?
Oh no.
Is the approximation greater than or less than the actual function value? So, is the approximation greater or less than the actual value? How do you know? All right, in order to determine this, you have to learn something, and it's a concept we have not discussed yet, and you will not be able to figure this out analytically because you haven't learned how to determine this yet, but visually you'll be able to do it. But the homework, just so you know, there's one problem in your homework tonight that asks you this, and you will not have enough information to be able to figure it out.
Why you got
So, yeah, I know. So just you can make a guess if you want to. But here's the thing. How do we know? Do you guys remember when you talked about polygons in geometry, you talked about concave versus convex? And I always used to think of concave as like it's caved in, right?
I never learned the difference.
You never learned the difference? Okay.
I just guessed.
Okay.
Didn't prove out well.
Okay. Anyway, in this class, everything's concave. We're going to be talking about concavity. The concavity is actually the degree of curviness of the function, but it also tells you, depending on the sign, it tells you if the function is this way, like this, or this way, like this. So we have either a function can be concave up or concave down. Every single curve is made up of parts that are either concave up or concave down. The only thing that has no concavity is a line, right? Everything else, anything that has curviness to it, is either concave up or concave down. Concave up, I like to say up like a cup, down like a frown, right? Some people say up like a smile, down like a frown, but it doesn't rhyme, right? So I like up like a cup, down like a frown. So concave up functions are functions where if you poured something in, they would hold water. Concave down, you can pour, it's just going to splatter everywhere, right? So anyway, this function is concave up. So if a function is concave up, this means that the tangent line approximation, will be less than the actual value. If it's concave down, then the approximation will be greater than the actual value. Now, why is that? Well, if you look at a concave up function and we drew a tangent line anywhere on a concave up function, what happens is when you draw a tangent line, the tangent line is actually below the function, right? So unless you're at the point of tangency, anywhere else, the value on the line will be below the value on the curve. So the approximation will be less than the actual function value. Does that make sense? Yeah? No?
Yes.
Okay, it should. If it doesn't, there's your picture, right? Concave down, if you draw a tangent line on a concave down function, then the points on the line will always be higher than the points on the curve. So that approximation would be higher than the actual value. This actually works in reverse too. It's a way to prove concavity, concave up or down, is if the tangent line is below the function is concave up. If the tangent line is above the function is concave down.
So when you say the approximation value, that just means like the
value on the tangent line.
All right, and
the tangent line
actual value or the
the value on the function.
All right.
Yes. Okay. Does that make sense? All right.